All right, everybody, welcome to our last lesson on electron configuration and transitions. Today, we're going to wrap up our conversation with hybridization. Now, hybridization is one of the more difficult but rewarding concepts that is in chemistry, especially in this chapter. So, what I want us to do when we're thinking about hybridization, when you're listening to this video, I want you to really think outside the box, right? Like we've been talking about elements in such a very confined way, but here we're going to kind of break that chain up. I'm going to actually admit I've really been lying to you guys about the actual configuration of these electrons. Now, I didn't mean to be rude. I didn't want to lie to you, but I had to, and you'll see why. Okay? So hybridization. So let's just first kind of break down that word, right? So hybridization. So hybrid means we're probably going to be combining two things together, maybe some more of that. So combining a few things together. Ization is usually a process. So we're going to be combining a few things together, and let's see what this specifically entails. So I have a question posed on the screen, which is, what's the problem with our current model? Right? So what is the problem with our current model? Well, let's talk about this. So what I would like to do is I want us to draw out the electron configuration of carbon. All right, so carbon has 1, 2, 3, 4, 5, 6 electrons in its ground state. So this is how we've traditionally shown carbon's electron configuration. However, there seems to be an issue with this, right? I'm going to give you a hint of what the problem may be. So hint number one, there's two hints. Hint number one is that we know that CH4 is a molecule. Okay, so we know that CH4 is a molecule. That's methane. Hint number two is that in order for a bond to form, we need to have single unpaired electrons. All right, so I want you to take a second, try this out on your own. What am I trying to get at here with this question? What is the problem with our current model with the two hints that we know that methane exists, right? Carbon has 4 bonds to hydrogen. And 2 is that in order to form a bond with another molecule or another atom, we need to have an unpaired electron. All right, did you figure it out? Well, if you didn't, here's what it is. So when we're looking at our electron configuration of carbon, we notice that we only have 2 electrons here and here that are unpaired. So according to this model, we could only have a carbon atom that could form 2 bonds. But that contradicts what we just said with hint number 1, right? Because at this point, when we were first discovering the electron configuration diagram, by we I mean scientists that are far older or dead than I am, we discovered that methane already was a thing. We knew that carbon had 4 bonds. So this model was almost immediately thrown out. We knew that there was something missing because, again, in order for a bond to form, we need 2 electrons to overlap. In order for carbon to make a bond with hydrogen, I can kind of show you what I mean here. Imagine that this electron and this electron that's in blue have to come from hydrogen, okay? So how do we get 4 unpaired electrons out of this model? So how can we fix it? Well, you may have already been able to guess. Hybridization, right? So hybridization is going to allow us to find these 4 missing electrons, these 4 unpaired electrons, because we already have 2, we just need to free up maybe these 2. And we'll talk about why all of this adds up and why all of this makes sense. So let's go ahead and go on to the hybridization component. So again, we have our traditional carbon ground state configuration, all right? But now what we're gonna do is we're gonna undergo this process of hybridization. Now, what you may have noticed is that on the right side of this hybridization process, I still have my 1s orbital saved, right? Can you think about why we didn't even touch the 1s orbital? Do you remember what we talked about with the noble gas configurations? Right? It's because it's super stable, right? The 1s is called the core electrons, right? So whenever we passed helium, those electrons are like, I'm done. I do not want to react. I'm super satisfied with where I'm at, super low energy. So they're not going to react. They're not going to be a part of this process, okay? However, everything else that is called the valence electrons, the things that are not a part of this process, are going to go into this hybridization mix. Okay? So what we're going to do is we're going to think of it in a kind of unique way, in that we have one s orbital and we have 3 p orbitals here, right? These are orbitals. One of these orbitals is unpaired, right? So we have a room that's completely empty that could be occupied, right? We have a completely empty room for no reason, right? Elements don't like wasting space if they don't have to. They'd much rather distribute that space if they can. And they also notice that, well, these 2s electrons, right? These 2s electrons, these two 2s electrons, both of them are at a lower energy. Now, the element, unlike the electrons, are much more keen on making sure that everybody's equal. Okay, they want every electron to be at an equal energy state if possible. So what this shell, this n equals 2 shell, is going to do is it's going to take all the orbitals it can. In this case, it's going to be these 4. Oops. It's going to be these 4 here. All right, and think of them as like we're going to mash them up. Okay, so we're going to take all 4 of these orbitals and we're going to mix them together. So we're mixing together one s orbital and 3 p orbitals. Okay, now when we're mixing them together, think of them like Play-Doh, right? So let's say s is green Play-Doh and p is, let's make it pink. I was going to say silver, but silver. Yeah, let's do silver and pink Play-Doh. Right, so we take silver and pink Play-Doh. We have 3 handfuls of pink Play-Doh and only 1 handful of silver Play-Doh. And we mix them together, for hours, right? Eventually, it's going to become this uniform color, right? This mostly pink, but somewhat silver elements, right? So I would ask you, what percentage of that Play-Doh dough is made out of silver? Well, your answer would be, well, 25%, right? So this is what we call 25% S character. Okay, so S character, and then the remaining is obviously P for pink, so the 75% P character. All right, and now I know you may not know what that means, but these attributes play a big role in reactivity if you were to move on to upper level chemistry in your future. All right, so just keep that in the back of your head. So when we're mixing these together, right, we're mixing 1s and 3p. And so the way that we denote these new orbitals is, one, they're all going to be equal in energy. So we take those 4 pieces of Play-Doh that we put together, the 3 pink and the 1 silver, we mix them together so that they're uniform. Well, that we know that they're all going to be the same energy. Now the 2 P's were a little bit higher in energy and the 2S was a little bit lower, so they should equal out somewhere in the middle. So it should look something like this, somewhere in the middle of where they once were. And we know that we had 1 s orbital, but we also included 3 p orbitals. Okay, so 1s, 3p, 1s, 3p, 1s, 3p. All right, so this is what we call sp3 hybridized. All right, so these orbitals have been sp3 hybridized. Okay, and this hybridization, again, allows us to kind of combine the relative energies of these 2 types of orbitals, the 2p orbitals and the s orbitals. So if we look here, the p orbitals are here and the 2s's are here. And if we come over here, they're somewhere in between, okay? So that's kind of the energy reference that I want you to get, because remember, the s orbitals are lower in energy, so they're bringing down the p's, but the p's are higher in energy, so it's bringing up the s. So they kind of mix out somewhere in the middle. So now the question is, well, what's the layout? Well, that's my question to you. Where would these electrons fall in this distribution, this new hybrid model? Take a second and think about it. Where would these new electrons fall? Would it be 2 in the first one? Would it be all 4 all spread out? Or would it be all 4 in the fourth one? How does it look? All right. So this actually applies very similarly to the same question I posed to you guys earlier, which was, well, these are all 4 equal rooms. So whenever you have an electron that comes in, they're just going to take an empty room. Well, how many electrons did we have? We had 1, 2, 3, 4. We had 4 electrons. And we just so happened to have 4 rooms. All right, so now let's go back to that question we mentioned earlier. What was the problem with our current model? The problem was we didn't have enough unpaired electrons to prove that methane exists, because we knew that methane existed, so our models needed to be correct. Well, look at this. We now have those 4 unpaired electrons. So this is a much better representation of our carbon atom in terms of reactivity. Okay, so when carbon's bound to other elements, so let's say hydrogen, if you did its electron configuration, right, here's your E, here's your 1s, it only has 1 electron. That 1 electron is going to combine with that sp3 hybridized electron or orbital. All right, and we could do that 4 more times for each different hydrogen. So I'm going to write the 4 hydrogens, each of them apply here. Okay, kind of cool, right? It all should be pretty logical. It all makes sense. All right, so last part. Nitrogen tends to have a lone pair. So for example, ammonia, I'm sure you've heard a lot about it. Ammonia looks like this. It has a nitrogen, 3 hydrogens, but the unique thing about ammonia is that it has a lone pair. Now, I know we haven't really talked about lone pairs yet, but just think of it as you have 2 electrons that aren't in a bond with another element. So they're just like being bound by nitrogen. So let's work on this one together. Let's take our original ground state configuration of an electron configuration of nitrogen. So nitrogen has 1 more electron than carbon. Okay, so let's think about why would nitrogen have a lone pair typically? So just like before, the 1s electrons are not going to react. They're going to stay the same. And let's do the exact same process again. So we combine those 3 2p's and the 1 2s, and we get these sp3 hybrid orbitals. However, what you may notice, also, by the way, I forgot to mention, these are technically 2 sp3 because we're in the second shell, but that's a little redundant in our case, so I'm just going to ignore it. Okay, so we have these 4 sp3, but look, we have 1 extra electron this time. So 1, 2, 3, 4, 5. Let's fill them in. 1, 2, 3, 4, 5. All right, so why do we have a lone pair? So now think for 1 second, what is unique about this electron configuration that makes hydrogen have a lone pair? Right, it's this right here, this guy, bam, bam, boom, boom, right there. Look, it has already a filled orbital. There's no way for it to bond. Right? There's no space for another electron. Remember, only orbitals can have a maximum of 2. That will never be broken. Okay? So those lone pair here are these, electrons. Okay? That means these bonds are made up between a hydrogen electron and a nitrogen electron. So let's make these in green. So one of these is here. This is the hydrogen electron. And lastly, here. All right. So this is the electron configuration of nitrogen, what's shown in red here. Now, I hope that this kind of helped, paint some color, provide some color into what hybridization is in chemistry. This can typically be a very confusing segment for a lot of students. So just rewatch this video. And again, try to answer these questions. Try to think very intuitively about why an element would want to do this. What is the benefit? And always remember, everything in the universe wants to be lazy, okay? I hope this helped. I hope everybody has a great rest of your day, and I'll see you all soon. Bye-bye.